deriving the expression of divergence in spherical coordinates. Start with the definition of the divergence. Divergence for some vector function f defined to be so using a visualization, if this is the surface you want to do an integration, every point on the surface there is a f vector pointing some direction, let's say this direction, and there is a unit normal vector to the surface, this one. So what you gotta do is take a dot product of two. So take a height the cast by the normal unit vector, and then multiply those side by the element of the area of the surface. So what you get is sort of like a cylinder. So bunch of cylinder going outward or inward. Okay. So I define this operator on the vector function which make this scalar, and let's call it just arbitrarily divergence. I could have called this anything, okay? I could have called this a Jun's function like that. So name doesn't matter, it is just historical accident. So I define this symbol. So eliminating the integration sign, the limit of the volume element surrounded by the closed surface you're doing the integration approaches 0. Surface. So this is the definition of the divergence. So let's do it in the spherical coordinates. Now I have this surface, looks like a rectangle, and here's so this is really small surface, closed surface, which I'm gonna do an integration. So as you can see, the volume element is this one dr, and this one increasing this angle times the r, the length of this one, and this I just explained this, and this side is r sine this one, since I am taking the shadow cast by xy axis, this one. So this one is a sine r, and as you increase this one you get this side. Sorry, my explain wasn't clear, so I'm going to use a diagram. X, Y, Z. So here it is, and I'm going to define this angle as with this symbol, this angle as this symbol, as you. So the volume element is dr, and this one r, and this one r sine. Okay, so now let's take a dot product of the unit number, which is the r times f r. Only fr survive, fr component. But mind you, in this direction the argument for r is not just the r, but r plus dr times the volume element, which is this one and this one. But since I'm using it not just the r but r plus dr, I should use dr and this one, r plus dr sine. And in this decreasing r direction, the unit number vector pointing this one is minus r, and only r components of the f survive. And with this time, it is just the argument for the distance is just an r. So r times the volume element is the same, r2 sine. Oh, sorry, I forgot to multiply this by this one, and divided by the volume element, which is r2 sine. So for this is the definition of the partial derivative of f with respect to the r. First, let's do some cancelling. This expression on the denominator and numerator cancels, and the sign cancels. Therefore, we're left with r exponent 2 dr. So what I'm left with is this is just the definition of the partial derivative of the function f components of r times r2. So I have found out one component of the divergence. Not a component is just scalar, but one part of the divergence for spherical coordinates. Now let's try to find out this unit vector, which is increasing this angle. Let's call this just arbart. So as you increase the arbart, the unit vector pointing in the increasing arbart is this one. Therefore, take a dot product, only arbart component survive, and since it is here, it is not just an arbart, but arbart plus differential of arbart times the volume element, this one. So volume element is this one, dr plus d arbart times r minus, now this decreasing arbart unit vector pointing this direction. So volume element is dr, and divide this expression by the volume element, which is r2 sine arbart delta dr. Now cancelling the same thing, cancelling the r. So I'm left with as I said, I'm only indicating the argument where two argument is different, slightly different. So this is just the definition of the partial derivative with respect to arbart. So now let's compute this component. So this is the this is the decreasing, this angle, let's call this Einstein. Decreasing Einstein, increasing Einstein. So the unit vector pointing this, take a dot product of the fx, only Einstein component survive. And the argument is this. Let's do it first. This one is plus dr, and let's do with the components, the area components, which is this one, area components. So this will be dr plus r sine plus delta, oh shit, times the differential of the, so let me move this expression here. Minus this one, take a dot product, but since the unit vector is decreasing arbord, it becomes minus. Divide by the volume element. And let's cancel the common factor, dr. So I'm left with r And as you know, this is just a definition of the partial derivative with respect to differential of arbord. Therefore, so I got a messy expression for the divergence of vector field F in the spherical coordinates. Now I'm sorry it's so dirty, so let me rewrite it cleanly here. 1 over r2 partial derivative with respect to dr plus 1 over r. Yeah, so I have derived the expression for the divergence in the spherical coordinates. And now I encourage you to do the same. What I mean by that is making an intuitive figure that will make you understand this intuitively, and I encourage you, try to derive this expression seeing the figure seeing the toy you made. Okay, so thank you very much for listening. This my first demonstration of math and physics, and goodbye.